These are slides from the spring of 2019. I think I've done this previously, but time to revisit. So as mechanical design and creating a scope of work for your projects, we're going to be focused on, well, narrowly focused on creating parts and pieces and putting dimensions on them. But when we start getting to the project level, we're working with systems and going through and creating a completed project, not one particular piece, then it takes on a life of its own. It's where the product life cycle comes in. So things that we're going to be concerned with: always safety, the manufacturing processes, joining, fastening, and hardware, the physical, our environmental, and measuring inspections. And the how did we get here? Hundreds and thousands of years of different tools and different technologies, and as everything's evolved, that we'll see the next generation of machine tools and tooling and product development progress and evolve even further. So on safety, probably the one that comes up the most is pinch points. That anything that opens and closes has the potential to do some damage. We have rotating mass of RPM and torque, actuation, so linear movements, however those are created. We have force and frequency, the mass, tipping points. You do not want a high center of mass, so one of the engineering tools that we'll look at in SolidWorks for our measurements is to see where that center of mass is. Temperatures, too hot or too cold, not good. Shearing and sharpness, some machines are meant to do that, but human involvement is usually a bad thing. Sound levels, of course, decibels and hearing, always a consideration, and safe work zones. So the considerations are guarding, e-stops, being able to isolate power, meaning in certain cases, hydraulics, electrical, pneumatic, sometimes even water. I mean, anything that is generating those forces has to be able to isolate and safely shut down the machine. All right, so our manufacturing processes: sawing, filing, drilling, shearing, milling, turning, grinding. EDM, electrical discharge machining, uses a wire and electrical charge to degrade material, holds very good tolerances. Finish, maybe not so much. Decent finish, but it's able to go through very hard materials. Not unlike plasma, laser, where you're generating electrical or a beam to perform the cutting. Water jet uses water and a fine media powder, so sand, to cut material. And then polishing comes down to sanding, buffing, and even electro-polishing, the different types of finish of plates, anodize, chemfill, oxidation, powder coating. And a lot of these are material dependent. We're going to be able to anodize aluminum and camfill, but steel is going to be black oxide. You can powder coat. Sometimes they need a base coat. Electroplating, chrome being the kind of a general electroplating process, usually needs to have a base of nickel attached to the material first. So different levels, different processes depending on what you want to end up with. The precision and accuracy, if we know that we're going to be doing grinding, then our milling and drilling processes have to leave enough material that after it's hardened, after we've done those processes, that the grinding and the finish machining will have enough material to remove. In the case of anodized, builds up a little bit, black oxide not so much. But if we're powder coating, depending on how much powder coat, you may get 10 to 20 thousandths, so half a millimeter of buildup that has to be taken into consideration. Electroplating is usually in the thousandths as well. And of course, the surface finish is how much waviness, how much flatness, and pretty much being able to control those end results. All right, our joining is going to consist of screws, bolts, and nuts. And the difference between the screws and the bolts and nuts is the screw feeds into the material, where the bolt and nuts, the material has through holes that the compressive force is between those two items rather than the part and the item. So, and then washers are kind of a wear surface that, as I'm tightening the nut or I'm tightening the screw, I don't want to gall into the material, so I'm going to put a washer in it. Sometimes the washers can be lock washers. If it's a high vibration situation, then the washers are always going to be able to perform that secondary function. Pins for locating, clips and rivets for retaining, bearings and bushings for rotating. Bearings, meaning ball bearings, needle bearings, are going to be higher RPM. Bushings are going to be like solid bronze, usually oil embedded into the bronze, so lower RPM may take more load. O-ring seals and gaskets, so the air stays out or in depending on whether you're dealing with pressure or vacuum, and same with the seals and gaskets with liquid. Extrusions, and we'll deal with a little bit with extrusions, but basically aluminum erector sets, so that we can build frames fairly easy and build whatever geometry we need. And then welding, usually with steels, but of course with the TIG processes and moving further than that, then of course aluminum, being able to make those joints. All right, so the mechanical fit becomes our concern. Is that in the screw category, are we dealing with hex heads? Are we going to do socketed cap screws? Are we going to do Phillips flat? I mean, there's so many choices. If you've ever walked through the hardware store down the nuts, bolts, and screws aisle, you know that there's all the bins with all the different sizes, all the different lengths, and even to the point of the grades of bolt for their applications. So done the threads elsewhere, and would just mention those again. Probably the main thing for the machine screws, the fractional and the metric, are pretty straightforward on the major diameters to understand how big it is. If you see a machine screw 0 through number 12, it's going to be smaller than a 1/4 inch. And the formula, that first number times 13 plus 60, giving you the major diameter, that's a really handy tool to have in your ready to go. So the physical side, on the static and dynamic forces, if we're dealing with static, it's meaning stationary. It's not really intended to move. Where dynamic, we're looking at that motion, having it perform some type of work. So forces, pressures, torques, vibration, frequency, acceleration, thermal conductivity, electrical conductivity. Mentioned the anodize. Anodize is a way for aluminum to reduce the amount of electrical conductivity. It may not completely eliminate it, but it certainly is a barrier. And then fluid and flow. So these are where we get into the finite element analysis or simulations that we're looking for kind of the gross errors. I don't expect my simulations to tell me everything. I cannot account for every last detail in the process of using the software, but I can get enough of a sense that the direction I'm taking, I've either over-designed, overcompensated for materials, or undercompensated, and I need to beef it up a little bit or can reduce it down. On our environmental, we're concerned about, is it in a corrosive environment? Is there any outgassing restrictions? What are the lubrication requirements? Hot and cold thermals, toxicity and reactivity to the environment. Also, is the machine creating any of those environmental conditions, and how do we manage, and what kind of regulations does it fall under? So the product life cycle management from beginning to end, from the purchasing of the materials, going through the design, doing the manufacturing, assembly, putting it out into the industry, and having it operate for a number of years, and then how is it going to be disposed of? All right, so our standards and standards organization, so the international system, ANSI is our sanctioning body, so the National Standards Institute takes the specifications from the Society of Manufacturing Engineers, the American Society of Mechanical Engineers, Automotive Engineers, brings those into that group and says these are the standards, so that we have that direction common to all industries. And then of course metric and inch, and the consideration again, alignment and consistency. With our measuring and inspection tools, we would have the scales, rules, and tapes. Just different ways of having the same convenient inch, millimeter references. Calipers are going to go one level further. So if I said I had an inch scale, I would realistically be able to a 32nd of an inch would be a reasonable measurement. Maybe could get to a 64th, but really that 60 thousandths, millimeter and a half is going to be doing pretty good with a scale, ruler, tape. Calipers are going to be in the thousandths of an inch, but again, depending on who's using and quality of the calipers and the environmental considerations, calipers are well within that plus or minus 5 range. Micrometers then, because of the way that they work, are going to take us into that plus or minus 5/10 of a thousandth, 0.0005. And consistently, the digital micrometers measuring to 50 millionths, we would like to be one order of magnitude on our measuring instrument above what we need to measure. So if I want to measure tenths, having a digital micrometer that can measure 50 millionths or a half of a tenth of a thousandth would is an advantage. Protractors for angles, also for angles, sine bars, and gauge blocks. Gauge blocks are handy for measuring interior geometries in the thousandth range as far as the no-go gauge. Plus minus gauge pens, same thing. The plus minus is also intense. So if I have a 250 1/4" pin, I would expect the plus to maybe measure 2 to 3/10 of a thousandths over, and the minus to measure 2 to 3/10 of a thousandth under. So I'm still within that range, and I can say that I'm in the tolerance zone of thousandths of an inch with that go no-go. Optical comparator uses lenses and a light source to project the geometry onto a screen, and then measuring tools to verify, visually verify those items. You get into the vision systems and probing, then basically a computer is doing the same thing as an optical comparator. And the coordinate measuring machines then take it up to another level where we're taking the geometry out of our solid modeler, putting it into the CMM system that will create datums and perform the measurements on that machine and generate a report. For our documentation, I think I mentioned in my career we've been talking about a paperless manufacturing for quite a while. We've made progress, but the reality is the shop is, no matter how clean, there's still coolants, oils, chips, materials that computers, tablets are certainly more survivable today, but pretty much are not the same as just having a piece of paper in front of you with those dimensions. So DimExpert and MBD, model-based definition, are pretty much the same, in the same category now. We'll see those two tabs in SolidWorks. The tolerance analysis is a stack up. We basically can do the same thing. If I need to generate a report, then I would use the tolerance analysis. We have the drawing modules that we can work from to create our document templates, and title blocks have all that information in to generate our paper hard copy as an output. The paperless then would be whichever modeler you're using. We can output to PDF or eDrawings or any number of viewers, and the 2D viewer is also PDF and eDrawings. So as a scope of work, all of this comes in, and sometimes it's 20-30 seconds of just thinking about what this item, what this product's going to do. And then the next step is the quotes and the estimate. How much is it going to cost? Is there a feasibility that if we take this to market, is it a one-off for a customer to perform a specific function? Are we going to make one or many? So when we talk about CAM, the computer-aided manufacturing, one of my first questions always is, am I making 1, 10, 100, 1,000, or this machine is going to run this part forever? In which case, that is how I optimize. And so optimizing for that direction is kind of the goal. And then of course the working drawings that we, depending on what we're dealing with, output. So scope of work sounds complex, but really a lot of these questions you're going to answer in the first 5 minutes, and as you go through, it's just something to keep in the back of your mind, that this the part that you're drawing detail fits into a larger system. So if you're only seeing a portion of this, that's your portion of it, that's your considerations, but need to also, I guess that's the other one I need to put in here, is the dimensioning and tolerance. And we talk about the standards and the ASME Y14.5 geometric dimensioning and tolerancing, which geometric and standard dimensions are a part of. When we sit down and actually do those tolerances, and a lot of the drawing videos that I made, we talk about iterations. The first pass is creating the view. The second pass is applying the basic dimensions. The third pass is applying the tolerances. Fourth pass is, does it need to be geometrically toleranced to hold those to hold that that geometry at a higher level. So we will revisit these on a regular basis. Again, this is more about terminology and having heard it, process it, and be able to utilize it when it comes up.